Today we're going to talk about area. So we're going to start off just with a simple graph, and let's just look at y equals x squared, and let's go on the interval from 0, and let's just go up to 2. Now if we're going to approximate this area, we'd use n rectangles, where the width of each rectangle would then be 2 minus 0 over n, or 2 over n. And then we'd have to decide between our upper sum and our lower sum. And I think for this, what I'm going to do is go with an upper sum, because that allows me to use the right endpoint, which is a little simpler algebraically. So our right endpoint, which we know is delta xi plus a, so 2 over ni plus 0. So that's our right endpoint. And we're going to approximate the area of this graph by finding an upper sum. So let's start with the sum as I goes from 1 to n of the base and the height of each rectangle. So the base is our delta x, so that's 2 over n, and the height is f of our right endpoint. So I can take out that 2 over n. And if we evaluate 2i, or f of 2i over n, we're just squaring it. So it's 2i over n squared. That's because our function is y equals x squared. And if we take all the constants out, we get, let's see, 8 over n cubed, as I goes from 1 to n, of I squared. We have a formula for that. So 8 over n cubed times n plus 1, 2n plus 1 over 6. We can simplify that a little. One of these n's, this can be a 3, this can be a 4. And if we distribute everything, first we have 2n squared times 4, which is 8n squared. Our middle term would be 3n times 4, which is 12n. And then our last term here would be 1 times 4, all over 3n squared. Now, what we're looking at here is our upper sum, because we were over approximating. So this right here is our upper sum, which will give us an approximation of the area using n rectangles. So we could use this formula. We can set n equal to 10 and find an over approximation using 10 rectangles, or however many as we want. But what we're going to do today is try to get an exact area, and in order to do that, we'd need infinitely many rectangles. And in order to find the area using infinitely many rectangles, we use the limit. So the limit as n goes to infinity of 8n squared plus 12n plus 4 over 3n squared. You can evaluate this however you want. We can either divide by the largest powered n in the denominator, we can use L'Hopital's rule, or we can remember that if the degree of the numerator is equal to that of the denominator, that the limit is just the ratio of the leading coefficients. So in this case, the exact area under this curve between 0 and 2, the exact area is equal to 8/3. Now, if we used the left endpoint, we would have ended up with a different expression up here, because that would have given us the lower sum, but the limit should still be equal, because whether we over approximate or under approximate, once we use infinitely many rectangles, we should have the same area. So our definition of area is the limit as n approaches infinity of the sum of the areas of the rectangle. So the areas would be base times height, where the height is f of some expression I'm calling c sub I, where c sub I that we're using is either the left endpoint or the right endpoint. So that's c sub I as the height, and the base is delta x.